Hello, D Block. Today I'm going to be talking to you about chemical bonding, as you can see. And something to consider here is, as you're looking at this screencast, I want you to take a moment and look around the room that you see in front of you. And I want you to notice that everything that you see in front of you is made up of chemicals. But what's interesting is that for the most part, none of those chemicals are simply pure elements. So why is that the case? Why is it that we don't see a lot of pure elements? For example, you don't see pure neon cruising around the place right now. You don't see, well, you might see pure gold if you see some jewelry, or even that though isn't pure. There are some components to it that make it sort of what's called an alloy. But you certainly don't see pure sodium. And the reason why I know you don't see pure sodium is that it's highly explosive. So if you had pure sodium near you, you'd be in a lot of trouble. And the reason that's the case is that elements typically aren't in pure form because they bond to other elements. They chemically turn into a compound. Now, we've touched on this briefly when we talked about, in the beginning, the concept of pure substances versus those things that are mixtures. But we did consider compounds to be pure substances in the way that a compound has a unique set of chemical and physical properties, not unlike elements that have a unique set of chemical and physical properties. However, the difference, obviously, between an element and a compound is that a compound consists of two or more different elements combined together and bonded together. So let's talk about that concept of bonding together and what it actually means. I certainly don't need to remind you of the fact that an atom consists of a nucleus containing neutrons and protons, surrounded by electrons in orbitals around that nucleus, and also that there are these things called valence electrons, which are the electrons in the outermost shell or orbital of a particular atom. And in fact, what you should know is that it's exactly these particular electrons, let's say this one or this one, or this one or this one, that are involved in the process of chemical bonding. So let's slow down a moment there and take a closer look again at this idea of the valence electrons. Don't forget that the valence electrons are the outermost electrons that are outside of an atom's noble gas core. And it's those valence electrons, as I just said moments ago, that are involved in chemical reactions. And in fact, those valence electrons are largely what's responsible for determining the nature or the chemical behavior of a particular atom. So, let's say we take the group 2. So, let me just point to this area right here. So, this group 2 set of atoms right here. So, looking at that, what are the valence electrons for this dude right here? Let's take in particular magnesium for a moment here. The noble gas core of magnesium is neon. Okay? And what that means is, if you look at the number of electrons that are associated with magnesium, we have 12. Right? 12. Oh boy, that looks hideous. Let me erase that. 12 electrons to go with the 12 protons to make it a neutral atom. And you can see here, associated with neon, we have 10. And if 10 are at the core, then we're going to have an additional 2 as the valence electrons for magnesium. Okay? So there are 2 valence electrons associated with magnesium. Let's then take a look at, say, something like sulfur. Okay? And if we look at sulfur, this is a little bit different. With sulfur, you can see that we have 16 electrons to balance out with the 16 protons. Yet neon is still the core for sulfur. What does that mean? Well, again, you just subtract away the core okay, the noble gas core, from 16, which is 10, and that gives you 6. So that means sulfur has 6 valence electrons. That's different from magnesium, which has 2 valence electrons. Okay, don't forget that piece. Now I want you to imagine something that you deal with every day. Here I have a pair of socks that's just come out of the dryer. And as you all know, if it's say a winter day, when you pull that pair of socks out of the dryer, the thing will stick to just about anything. And we all know that this is caused by static electricity. And the whole concept of static electricity is based on the idea that we have both a positive and a negatively charged, in this case, sock or pair of pants. So imagine for a moment that this sock is positively charged. You have no problem with the concept that that positively charged sock might actually be attached to a slightly negatively charged t-shirt. Okay? Because we understand that positive and negative attract to one another. We've already understood that for ages. Well, now I want you to consider, instead of socks and t-shirts, I want you to consider elements. Now, we've established that there are certain elements that form particular ions. And in fact, let's take, for example, I'm going to go backwards a little bit here. Let's go back to that magnesium. Magnesium, as you may recall, likes to form a +2 charge. Okay, so we take magnesium, and we know it forms a +2 charge. Think of that as being like the sock. And we also know, again, let's go back to here, that sulfur prefers to form a -2 charge. So let's go ahead and make our sulfur over here with a 2- charge. So that would be like the blue shirt for our sulfur. Now, it wouldn't be too much of a stretch for you guys to imagine that these two things would be attracted to each other. Oh, I left behind a little bit of my 2 there. Yikes. There we go. This magnesium... What's going on? Alright, here we go. The magnesium would want to come in contact with the sulfur because they're oppositely charged. They really like each other. And don't forget that we have names for this. This is called the cation, and this one's called the anion, because it's negatively charged. Okay? Now here's something else to consider. Don't forget that when we're talking about an s orbital, we can fit as many as 2 electrons into an s orbital. So let's just say this is like the 2s orbital. Okay? And we also know that the p orbital can hold as many as 6. Okay, and we'll just call this the 2p. Now let's imagine for a moment that we have an atom that has a filled 2s and a 2p set of orbitals. It's pretty happy. But you should also know that that would be potentially, or definitely, those would be the valence electrons. Now, let's for a moment zap this right here, and instead of having a 6, let's say we have a 4. All right? So under normal circumstances, P can hold a total of 6. And together, these 2 outer orbitals can hold a total of 8. Okay? And I want you to think about sulfur now for a moment. Let's go back. If you look at sulfur here, we know that sulfur has an electron configuration that needs to go up to 16, right? So let's go ahead and build this up for a moment. Okay, I'm just shifted over here to get some more room. So I have 1s2, 2s2, 2p6, 3s2, 3p, hold on, let me add this up. So I have 10, 11, 12, wait, what do I need to be at again? 16. So I need to add 4 more to this thing. And don't forget, what can my p hold? It can hold as many as 6. But this right now is sulfur. Yeah? And this represents sulfur because I have 16 electrons associated with, combined with my 16 protons to be a balanced and neutral atom of sulfur. But clearly, sulfur has room in its p sublevel, its 3p sublevel, for 2 more electrons. And in fact, you should understand that atoms really like to fill up their final orbital over here. Sorry about that. I had to go deal with the kids. And when I mean final, I mean their outermost orbital. So let's for a moment take a look at something else. Let's take a look at, say, sodium. So with sodium, I have my nucleus in there, and I'm also going to have, let's see, is it 11? Yeah, 11 electrons cruising around this thing. All right, so I'm just going to make this a little simpler than, obviously I need to draw this in more orbital form, but to keep myself sane here, I'm just going to put negative signs surrounding this thing. So I'm going to have 1, 2, 3, 4, 5, 6, 7, 8. Wait, what does sodium have? Yeah, it does have 11. Okay. And I want you to imagine this is sort of an orbital situation like this, even though it looks like an orbit. Pretend it doesn't. It's going to make my life much easier, though, if we just suspend what we really know about orbitals for just a moment. And then we're going to have an outer orbital that's outside of that needs to have 2 more electrons. I'll go ahead and circle up all these electrons here, these negatively charged fellas, just to make it easier for you to see them. So I have a total of, oh wait, is that just 1, 2, 3, 4, 5, 6, 7, 8, 9, 10? Oh, I need one more. Okay. Negative, there we go. 11. So this represents my sodium atom. You know what? I actually kind of made a mess of this. No. Oh, Chang, you suck. Let me erase this thing and start again, just because I just totally confused this. I need to actually have us focus just on the outermost orbitals of my sodium ion. So let me quickly go back here and fix this. Okay, that's better. So what I have in here, and I'm just going to point to it right here. This electron and this electron are my 1s, and there are 2 of them in there. And then I have my 8 surrounding that, so that's going to be... Shoot, I'm making a mess of this. Well, let's keep moving. So actually, this first one, I'm going to point to this right here. This second ring actually is going to be at my principal quantum number 2. So this would be my 2p, and it's totally filled. But since there are 8 of them, you have to understand that's not only just my 2p, but this actually contains my 2s as well. So 2s and 2p are represented here with this 8. Okay, whereas this is only my first quantum level with just 2. And then outside of that, I have my 3s orbital going on here, and I only have 1 electron floating around out there. Now, it could either do one of 2 things. If it likes to have that outermost shell filled, right, it could either gain 7 electrons to have 8, to have 8 of them, or it could lose this 1 electron right here to then go back to have its outermost shell having 8. And obviously, it makes much more sense for us to lose that single electron that's in the 3rd principal quantum number. And so that's exactly what the sodium does. Okay? The sodium is going to lose... Do I have room over here? Oh, darn it, I don't. So I'm going to go in this direction. The sodium is going to lose that outermost electron, and it's essentially going to be just this area right in here. So let me collect it up. Select this whole thing here. You can't see I'm doing that, but I'm going to copy it and paste it, and boom. There I have sodium, which still has, it's going to have its 11 protons, but now it has 1 fewer electron, right? It only has 10 electrons, and as a result of that, it's no longer a neutral atom. It has sodium with a +1 charge. Okay? Now, if it lost an electron, it just can't lose an electron for free. It needs to lose it to something. And in this case, it would lose it to its pal, and its pal in this case happens to be chlorine. Now chlorine, for its outermost valence electrons, or just simply its valence electrons, it actually has 7 electrons out there in its outermost orbital. Now, for it to complete and have 8 in its outermost orbital, it would like to have an electron, because it's missing one. You could imagine there's sort of a hole hanging out right there, and it would love to have an electron. But it just can't grab any electron. It needs to find an electron from a willing participant in a reaction. And lo and behold, that brings us over to here, our sodium ion that wants to get rid of one, or our sodium element, I should say, our atom that would like to get rid of one, and our chlorine who would like to have one. Now, what do you think is going to happen? You guessed it. They're going to share. It's actually more than share. It's going to be a complete transfer. And by transferring the electron from our sodium over to this chlorine, both atoms are now going to be totally satisfied because they will have 8 electrons in their outermost orbital. Now, this concept of wanting to have a full set of valence electrons, which in the case of what we're studying right now is 8, is called the octet rule. It's the last thing I'm going to talk about before signing off. And what the octet rule states is that atoms tend to lose or gain or share electrons in order to acquire a full set of valence electrons. I'll write that down, and I'm going to stop it right here. Okay, there you have it written out. I will see you guys tomorrow. See ya.